Let's look at another example of a collision. Two cars are on the street. So car number 1 is going to be moving at some velocity to the right, and car number 2 is going to be stationary. Now, car number 1 must not be paying much attention because it is going to slam into car number 2. And when it does, that forces both cars to begin moving. Pretty typical collision problem. You guys have seen ones like this before in your homework. And we know that this combined velocity of both car 1 and car 2 is going to be some velocity greater than 0 in the same direction as car 1 was originally. Now, if we look at everything, we see that conservation of momentum, right? But if we look just at car number 2, the one that is in red, well, we see that originally it has a velocity of 0, which also means that it has a momentum of 0. But if we just look at car 2 after, well, now it's got some velocity greater than 0, therefore its momentum is greater than 0. That was weird. So we don't see conservation of momentum when we look at just the red car, and that's fine, right? We only see conservation whenever we look at everything in a system, and if we only look at part of the system, then we can see changes in things like momentum. Now this has a name. A change in momentum is also called an impulse. Okay? Now how can we calculate this? Well, we know that momentum is equal to mass times velocity. So in order for us to change that momentum, it's not often because we change the mass. Most of the time we get a change in momentum because we have changed that velocity, as we did in the example above. So if I ever ask you guys to calculate a change in momentum, I'm asking you to tell me what the mass times the change in velocity is. Now, change in momentum is also called an impulse, and really this is an extension of Newton's second law. So if you recall from last semester, Newton's second law was F net equals m times a. And also from last semester, hopefully you remember that we have lots of ways that we can calculate an acceleration. Using our knowledge of kinematics, we could think of Vf equals a delta t plus Vi, and we could rearrange that Vf equals a delta t plus Vi in order to read as acceleration equals Vf minus Vi divided by delta t. Okay, so Vf minus Vi over delta t is just a rearrangement of Vf equals a delta t plus Vi. Now, we also know that anytime we do final minus initial, that is the same thing as change in. So we could also say that this acceleration is the same as change in velocity divided by change in time. And what we're going to do is we're going to take that idea of acceleration being changed in velocity divided by change in time. We're going to substitute that into Newton's second law. And when we do, we end up seeing that net force is equal to mass times change in velocity divided by change in time. And we see in there something that looks oh so familiar, don't we? It's that mass times change in velocity. We just saw that. We know that mass times change in velocity is the same thing as a change in momentum. So, to get that all by itself, let's multiply the delta t to the other side, and we end up seeing that net force multiplied by change in time is equal to mass times change in velocity. And this is called the impulse momentum theorem. Impulse momentum theorem. The reason why it is called the impulse momentum theorem is because it's really reminding us that change in momentum is also the same thing as impulse. And the impulse part of it is the net force times change in time. The momentum part of it is the mass times the change in velocity. So if I ever ask you to calculate an impulse, you could calculate it by doing F net times delta t. But since F net delta t is the same thing as m delta v, you could use that to calculate an impulse as well. Same thing with a change in momentum. If I ask you to calculate a change in momentum, you could find that by doing mass times change in velocity. But since that is the same thing as F net times delta t, you could do that as well. Okay? The impulse momentum theorem says that those two things are the same. So to practice this idea of impulse a little bit, we're going to do a couple practice problems. Exercise 4, Jennifer, who has a mass of 50 kilograms, is riding at 35 meters per second in her red sports car when she suddenly must slam on the brakes in order to avoid hitting a deer crossing the road. She strikes the airbag. It brings her body to a stop in 0.5 seconds. What average force does the seatbelt exert on her? So if we write out all of our knowns, we know that Jennifer has a mass of 50 kilograms. We know that she is going to change her speed from 35 meters per second down to 0, so her delta V is 35 meters per second. We know that this takes a time of 0.5 seconds, and I'm asking you to tell me what force is she going to experience. So if we look at those knowns, hopefully we see right away that those four knowns are present in the impulse momentum theorem. F net delta t is equal to m delta v. So if we put in what we know that time is 0.5 seconds, we know that her mass is 50 kilograms, we know that she's going to change her speed by 35 meters per second, well then we find that the net force that acts on Jennifer is 3,500 newtons. Now, is that going to kill Jennifer? Probably not. I think that's like 7 G's worth of force, so she's feeling 7 times her body weight, and it's going to be really uncomfortable, and she might even break some bones, but Jennifer will probably survive. In exercise 5, we are back with Jennifer again. She's still not wearing her seatbelt, but now she doesn't have an airbag. So it is now the windshield that will stop her head when she's trying to avoid hitting this deer. And the windshield is going to stop her head in 0.002 seconds. What is the average force that the windshield would exert on her? So we have almost the same set of knowns. We still have a mass of 50 kilograms. We still have a change in velocity of 35 meters per second, but now our time has dramatically decreased. It's now 0.002 seconds, and we want to know how much force is going to act on Jennifer. So, sounds like we're going to have to do a very similar calculation. We'll use the impulse momentum theorem. We'll put in 0.002 seconds as the time, and then we'll keep the 50 kilograms and 35 meters per second as her mass and change in velocity. And when we calculate this, we now find that it requires 875,000 newtons in order to stop Jennifer. And I gotta tell you, I mean, this is completely deadly. Jennifer will not survive that car crash. And the reason why I put this problem into our notes is because, you know, this is also a good reminder that you should always be using all the safety devices available to you. So please, 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 always wear your seatbelt. It's the difference between living and dying. Otherwise, let's go to exercise 6. We got a diagram that depicts before and after collision speeds of a car that hits a wall. In case A, the car bounces off the wall. In case B, the car crumples up and sticks to the wall. In which case is the change in velocity the greatest? So we know change in velocity is the same thing as final velocity minus initial velocity. So for car A, the final velocity is -4 meters per second. The initial velocity was 5 meters per second, giving car A a change in velocity of 9 meters per second. Car B stops, so its final velocity is 0 meters per second. It was also originally moving at 5 meters per second, so it experiences a change in velocity of -5 meters per second. So car A has a greater change in velocity because of that direction change, right? When it moves from one direction to the other direction, that's a huge change in velocity. In which case, would the change in momentum be the greatest? Well, we know that change in momentum is equal to mass times change in velocity. So since these two cars are identical, and since car A has a greater change in velocity, we would expect that A would have the greater change in momentum. After all, so if the masses are the same, velocity is the only thing that would determine how big its momentum was. In which case, is the impulse the greatest? Well, we know that change in momentum is the same thing as impulse. By the way, impulse is denoted by a capital letter J. I know that seems weird, but that's just the way they do it. So, since A has the greater change in momentum, we would expect that A would have greater impulse. And then finally, in which case is the force acting upon the car going to be the greatest, assuming that the contact times are the same? Well, we could figure this out by knowing that impulse is the same thing as net force times change in time. So if their changes in time are the same, then the one with the greatest impulse would then have the greatest force acting upon it.